So the next speaker is Professor Russel Reiter. Please.
Thank you very much. Firstly, I want to thank all the previous speakers for their effort to present them in English. Obviously, that's the language of science, but you people do an excellent job when you come here. Secondly, I wish we are talking to each other. Obviously, everyone in this audience understands oxidative stress, the importance of antioxidants. And it's unfortunate at a meeting like this that more people from outside of our specific group don't take advantage of this information. I think it's very important for health, general health, and possibly even for longevity. I think this is the wrong slide. Well, I can talk about this slide. This is what we conventionally think about when we think about melatonin. There you go. There you go. And what is represented here at the top of the image is melatonin production by the pineal gland. Typically, what is known about melatonin is produced in the pineal gland, released into the blood, and has circadian rhythm effects. And that is represented here. Well, nothing seems to work. But at any rate, none of these pointers work. Well, at any rate, at the top, you can see the release of melatonin into the CSF and in the blood. The concentrations in the CSF are significantly higher than in the blood, but in both cases, there's a circadian rhythm in the blood and in the tissue as a consequence of secretion of melatonin by the pineal gland. But the pineal gland is only a very small portion of the total melatonin load in an organism, including us. At the bottom is represented the other site of melatonin production, namely, it appears that melatonin is produced in the mitochondria of all cells in all organisms. And you have to realize that mitochondria go back to the very origin of eukaryotes when they ingested prokaryotes. Prokaryotes have the enzymes required for melatonin production. When they were engulfed by eukaryotes, they evolved into bacteria. The bacteria evolved into mitochondria, of course, and they retain the ability, so far as we know, to produce melatonin. As a consequence, every species that has existed ever or currently exists produces melatonin. This is very obvious in plants, in extremophiles, in all vertebrates, and in all animals, insects, and so forth. So every species in which it's been measured has been found to be produced. The difference between pineal melatonin and cellular melatonin is that cellular melatonin is never released into the blood. In other words, if you remove the pineal gland from animals, blood levels are minimal, but there's still ample levels in the tissues. And it's produced in the mitochondria, represented here, and it's released from the mitochondria and has intracellular actions. It may, may also be released and have some paracrine actions on adjacent cells, but generally we think of its non-releasable, never getting into the blood or into the cerebrospinal fluid. I already alluded to this, that 95% of the melatonin that is in your body is not of pineal origin. Represented here in red is the amount of melatonin produced in the pineal gland of vertebrates. It's about 5%, and that's a very generous estimate. The pineal, circadian, releasable, but only in vertebrates. Only vertebrates have a pineal gland, and they did not evolve. Vertebrates did not evolve until the Cambrian explosion about 520 million years ago. Melatonin existed 2 to 3 billion years ago. So melatonin existed billions of years before the pineal gland and vertebrates even evolved. And I said it's circadian regulation. In all species, melatonin is abundantly produced in mitochondria. It says multiple organs. Every organ that has a mitochondria, we presume it's produced in. Of course, non-circadian, non-releasable. It's not circadian rhythm regulated. It's a totally different system. And on the far right are the actions of this molecule. It's a very good antioxidant, anti-inflammatory agent, and antibacterial. There were 250 publications suggesting its use, in fact, in COVID. This illustrates some of the mitochondrial evidence. This is the work of, not our work, but rather that of Lieberman at the University of Pittsburgh. He isolated the mitochondria of the brain, of neurons, and it showed that the two enzymes, AANAT, ASMT, represented here at the bottom, serotonin is converted to N-acetylserotonin by AANAT, and then it's methylated to melatonin. Those two enzymes, you can see here, are expressed in the mitochondria of the brain cells. Also, the presence of 14-3-3 zeta chaperone is in there, which you would expect. All the other measurements are things that are not supposed to be in the mitochondria, and they are not, with the exception of COX-4, which is known to be in the mitochondria. So the mitochondrial preparation was very pure in this case. We had previously shown 3 years earlier that melatonin is in very high concentrations in mitochondria when you fractionate cells. We did liver and brain, and we found that the mitochondrial concentrations of melatonin far exceeded those in the cytosol, in the nucleus, or in the other membranes. So it appears that the mitochondria synthesize melatonin. Not every tissue has been tested, of course, but mitochondria have been found in the oocyte of when they ovulate in the female. The oocyte mitochondria give rise to all the mitochondria in the organism, and they contain the melatonin synthetic machinery. So we assume, not absolutely documented, that every tissue that has mitochondria has the ability to produce melatonin. If you digest the outer mitochondrial membrane with, I think it's proteinase K and digoxin, the melatonin content remains the same. In other words, in the mitochondria, the melatonin seems to be not in the intramembrane space, but rather in the matrix. Likewise, there is no circadian rhythm represented here. You can't see it very well. My pointer doesn't work, but the point is that in mitochondria, melatonin is not rhythmic. Of course, you people are all very familiar with this illustration. Oxygen is a major source, of course, of free radicals. A single electron reduction of oxygen produces superoxide anion radical, superoxide dismutase, converts it to hydrogen peroxide, and then in the presence of the Fenton reaction, the hydroxyl radical is produced. A hydroxyl radical theoretically accounts for 60 to 70% of all the damage inflicted in your body as a consequence of free radicals. As is shown in another presentation today, each of these has been shown to be scavenged by melatonin. Melatonin directly scavenges these molecules, but melatonin also has receptor-mediated actions to stimulate antioxidative enzymes. Superoxide dismutase, SOD, glutathione peroxidase, GPX, and glutathione reductase are also all promoted by melatonin. Besides this pathway to produce a hydroxyl radical, superoxide combines with the gaseous neurotransmitter nitric oxide to generate the peroxynitride anion. Peroxynitride is not a free radical, but it's a very potent oxidizing agent and extremely toxic, and scavenged by melatonin. Now, this is kind of an important point, I think. Of course, here's a mitochondria, here's the electron transport chain, and we know several studies, well, numerous studies, but several people have mentioned this, that electrons leak, especially from complex 1 and complex 3, and reduce ground state oxygen to superoxide anion radical. Well, these radicals have a very short half-life. For example, I don't know if you can read it down here, the hydroxyl radical has an estimated half-life of 10 to the minus 10 seconds. In other words, when these radicals are formed, they don't hang around and go looking for a molecule they damage. They damage in the immediate vicinity of where they are produced. In fact, it's called on-site damage. So what I've shown here on your right is I got a small circle around the inner mitochondrial membrane and enlarge it up here to show the electron transport chain and the production of free radicals, particularly the hydroxyl radical. And melatonin is present in the mitochondrial matrix. In other words, what could be better than having a potent antioxidant already in the matrix where the free radicals are generated? We think this is extremely important. This is referred to generally as the reaction cage of a free radical. They don't move around. They're produced, they damage. So the antioxidant has to be on site, has to be right there to prevent the damage. So having it in the mitochondria, we think is very important. I'm going to illustrate how this applies to the blood vascular system. There are many problems in the blood vascular system that have been mentioned already. Heart attack, involved ischemia, reperfusion injury, both hypoxia and hyperoxia, which are the extremes of ischemia reperfusion, cause oxidative damage. Of course, drug-mediated damage, doxorubicin, an anti-cancer agent, specifically designed to go into the mitochondria. The cardiomyocytes have very high concentrations of mitochondria compared to most other organs. So naturally, the heart is damaged when you take these severe drugs. And we know that melatonin prevents the toxicity of doxorubicin and other agents that fight cancer. Atherosclerosis is a very strong area of investigation relative to free radicals, and diabetes-related cardiovascular disease, primarily, again, that's atherosclerosis. But at any rate, these diseases are all known to be modified by melatonin. Here's an example of a study we did already in about 2016. I guess it's here. Oh, excuse me, I'm sorry. I shouldn't have done that. But at any rate, what we did was fed mice a high-fat diet, 3% cholesterol diet. They were, of course, APO double knockouts. And here's the control after 12 weeks of treatment with regular diet, no high cholesterol, then with cholesterol, and then with high cholesterol or high-fat diet and melatonin. And you can see grossly the difference. These are stimulated, stained with oil red O. Oil red O recognizes fat deposits, relatively fewer, not absent, but relatively fewer in the control, very significantly increased after a high-fat diet, and significantly reduced by melatonin. Histologically, that was easy to confirm, obviously, in high and low power magnification. You can see that there's more fat in the high-fat diet animals and reduced by melatonin. We also measured the extent of the aortic lesions, especially in the aortic arch. Turbulence in the aortic arch usually makes them more susceptible to atherosclerotic plaques, and you can see that on the right lower, extent of aortic lesions, very high in a high-fat diet, and depressed in the melatonin-treated animals. Likewise, the average plaque area in the aorta, the total aorta, was diminished as well. We did many, obviously, other studies on these animals, but I want to move on to some additional studies by other individuals. This study came out of China recently by Chen. It's also hidden down there. But this shows something very, very important. Plaque rupture. Atherosclerotic plaques form, but when they rupture, it is really devastating because the molecular debris escapes into the artery, clogs the artery, and most heart attacks are a consequence of ruptured plaques in these small arteries of the heart. And of course, the other tissue that is most grossly affected is the brain. That doesn't mean it doesn't occur in other tissues, but it is not as severe as in the heart and in the brain. But at any rate, as shown here on your left is what happens normally. Pathological smooth muscles proliferate, but they don't form collagen. What melatonin does on the right is cause the proliferation of the smooth muscle cells, but also upregulates their ability to produce collagen. You don't generally think of smooth muscle cells producing collagen, but in fact they can, and they're often called myofibroblasts. They produce collagen, and collagen forms a very firm plaque head or plaque crown or a hard plaque to prevent them from bursting. And the molecular processes are very well identified how this occurs. Of course, the smooth muscle cells are already in the subendothelial space, and if they proliferate, it's not good if they don't produce collagen because it puts pressure on the plaque, causing it to rupture, and the necrotic cores, represented here in blue, are also enlarged. This is a summary of a paper we just published recently showing the interaction of melatonin with atherosclerotic plaques and the likelihood of rupture. Obviously, I cannot reveal all of the proving data for this, but this is one longitudinal section of, say, a coronary artery. At the top is the arterial lumen in red, of course, and this is the developing plaque. Melatonin is known to inhibit the adhesion molecules, selectins and VCAMs, on the endothelial cells, which allow these cells, such as lymphocytes and monocytes, to stick and diapedese into the subendothelial space or into what is called a tunica intima. In the tunica intima, the monocytes are converted to macrophages, and unfortunately, macrophages can be very, very toxic if they are of the type 1. And converting them to type 2 is called polarization. Melatonin polarizes macrophages to the type 2, which are anti-inflammatory. The others are pro-inflammatory. So the fact that melatonin does this alone is very important. And that's been shown in many different circumstances. What the macrophages normally do is engulf the fat, and they rupture and form part of the necrotic core. These are called foam cells. Additionally, the lymphocytes, of course, generate free radicals, as shown down here, and as melatonin is a very strong, of course, free radical scavenger. Additionally, what happens is blood vessels, that red line with the bulbous top, that's blood vessels growing in. The tunica intima does not have any blood vessels. They come from the tunica media and the tunica adventitia, grow in here, and that enlarges the plaque core. But what's worse is when those blood vessels rupture. When they rupture, they, of course, bleed a lot, and also put pressure on the core. So that's what causes the eventual rupture of the plaque. So I remind you that what melatonin does is stimulate smooth muscles to advance collagen formation to convert soft plaques to hard plaques. Hard plaques are much less likely to rupture than our soft plaques. That is all represented here. Again, this is the result of all the studies, the actions of melatonin atherosclerotic plaques, preventing them from rupture. On this side are the systemic actions of melatonin. It reduces low-density cholesterol. I'm not totally convinced how much it does that. We have looked at that often. There are others reported that it does, but it does increase high-density cholesterol, which is generally referred to as good cholesterol. So this is a very important aspect. It inhibits the adhesion molecules I already mentioned. It reduces inflammation, reduces oxidative damage, prevents capillary ingrowth, prevents intraplaque hemorrhage, and reduces necrotic core, but importantly, improves melatonin synthesis. There are the molecular changes associated with these systemic effects, and those molecular changes have all been verified. For example, I told you selectin and VCAM are inhibited, monocyte chemotactin protein, the conversion or the polarization of the M2 to the M1 prevented. The M1 you do not want. It's highly inflammatory. PPARP, of course, we know PPARP delta is really a transcription factor and a receptor for melatonin. It is nuclear in the nucleus. It does bind melatonin as well, and it is noticeably depressed in individuals who have cardiovascular disease, as is melatonin. So both PPARP and melatonin are depressed in individuals that have cardiovascular disease. Giving melatonin upregulates PPARP and, in fact, converts soft to hard plaques. And the consequences of all this are listed at the bottom. You can see the other molecular events that are related to melatonin, all of which are either anti-inflammatory or antioxidant and improve the likelihood that your plaques will not rupture. That doesn't mean they won't. Improve the likelihood that they will not. These are some of the multiple actions of melatonin, as we know, in the cardiovascular system. Besides doing this, it prevents the stickiness of platelets. There are times when a plaque doesn't have to rupture. It just narrows the blood vessel to a point where not much can get through, and plaques can accumulate in there, stick together, and cause obstruction of blood flow that well. And melatonin also reduces the stickiness of, and reduces blood coagulation. This is why it was so highly recommended in COVID, because of diffuse intravascular coagulation. Melatonin is known to inhibit that, and that was one of the benefits. Additionally, melatonin, of course, is highly antiviral. It's been shown to inhibit many, many different viruses. Well, of course, like everyone else, we've done ischemia reperfusion of the heart, represented up here on the left top. This was done by work by Yundai Chin at the 301 Hospital in Beijing. In combination with us, we looked at obstruction of the anterior descending coronary artery. 2 days later, stained them with Evans blue. Evans blue is only taken up by surviving cells, and you can see that there's math of death of the cells in the heart unless they are given melatonin. And of course, the infarct volume, represented here by this graph, and then the stroke volume. In other words, not only was the heart preserved morphologically, but physiologically as well. And this is what I referred to before. These are these microthromboses in the small blood vessels that are a problem in COVID. And you can see that In the melatonin-treated animals, where the yellow writing is, there's none of that red stain, which represents these and the green background, of course, is troponin, which identifies cardiomyocytes. We've also have a clinical trial going on called the Maria trial, where we studied individuals which have a heart attack called STEMI, ST segment elevated myocardial infarction, a serious infarction, and as soon as possible after that, we put a catheter in the femoral vein, run it up in the heart, and do a balloon angioplasty to open the blood vessel and simultaneously inject melatonin to prevent the very severe damage that occurs as a consequence of reperfusion. Doing this, we have studied, it's been published in the American Journal of Cardiology, and if the injection of melatonin is done within the first 2 hours, the reduced damage to the heart is around 40%. After that, the prevention disappears because the damage is already done within this very short time. So it is imperative that if you're going to use it, it has to be done as soon as possible, but that is not always easy to do in considering where the individual may be when the accident happens. But these are studies that are ongoing. Melatonin is really a remarkable molecule. I showed you the circadian rhythm effects are a function of pineal melatonin, and for years, everyone thought that is melatonin, circadian rhythm regulation. In fact, it has remarkable and abundant other effects in all other organs. Melatonin is produced in the mitochondria of every cell. One of the cells that does not produce melatonin, presumably, is red blood cells they have no mitochondria. But also the cellular actions now are very well described, particularly at the mitochondrial level. In fact, ubiquination and proteasome protein degradation, of course, it's a good antioxidant. Apoptosis, whether it's ferroptosis, copraptosis, whatever apoptosis it is, melatonin will impact it. So that's kind of a summary of everything melatonin can do. I want to point out there are 100 patents on melatonin. I have none. I do not want any patents on melatonin. I do not sell melatonin products. I'm not here to sell you a melatonin product. I'm here to show you the data. I purposely stay away from a vested interest. Melatonin is generally beneficial to all systems. I remind you that as you age, your endogenous melatonin in your pineal gland and in your mitochondria diminishes markedly. So you are most vulnerable, and that point has been made also today. You are most vulnerable to oxidative stress as you age because you are losing one of your very best antioxidants during the course. Melatonin is widely used and has no toxic reactions. In very high dose, no LD50 has ever been done for melatonin, for example. LD50 is a lethal dose for 50% of the animals when you get the dose so high that it actually kills some of the animals. You can't do an LD50 for melatonin because you cannot kill an animal. 400 milligrams per kilogram body weight, the animal just shrugs it off. In humans, they say, there's a small percentage of people say, I got a headache or was a little dizzy. These subjective measurements are very difficult to evaluate, and of course, the placebo effect is very large in the human. Melatonin is inexpensive, but not patentable. That's unfortunate it's not patentable, because pharmaceutical industry has no interest. They cannot patent it, they cannot formulate it, and they will not make any money. Patents are no good on melatonin because it's not a patentable molecule. So anybody can sell it, anybody can use it. But I do not sell it. I do not have any patents. I do not want any patents. The patents are for use. Use patents are almost worthless. But at any rate, melatonin is a good, wholesome molecule. You lose it with age, And there's a lot of evidence that using it regularly, which in the United States, millions of people use melatonin, not for this reason, but for sleep. Melatonin is a circadian rhythm regulator that impacts sleep. I don't think it's very good at that, but that's why people use it. There may be other benefits. There was just a publication in the Proceedings of the National Academy of Sciences of the United States. There's a very large melatonin experiment going on by virtue of the fact that so many people take it. And what this study reported is that age-related macular degeneration, which is a high free radical-related disease, is much less common in people who use melatonin on a regular basis than compared to those who do not. That's a type of study that our epidemiologists, where are they when we need them? They could do these studies now because many people take melatonin, many people do not. And it would be obviously a big survey, but they could measure the incidence or the frequency of these diseases. With that information in hand, I thank you for your attention.